Hi, good morning, everyone. Thank you, Klaus, for the introduction. So just to reiterate, my name is Paul Jones. I'm application engineer with Zuken UK Limited, and today I'm going to go through the ECAD-MCAD collaboration with Designforce. So just to go over the agenda, I'm just going to go through a quick introduction. I'm going to outline some of the challenges that people face in regards to communicating from MCAD through into ECAD and back. Obviously, we want that transparency. How we can use IDF, we're going to go through some of the limitations, some of the pitfalls, this type of thing with using IDF. Then we're going to show some of the step files, so sort of some of the native formats that you can have from the mechanical system, how you import the mechanical data, some of the benefits of using step. Then I'm going to go into IDX data. So we're going to show things like how can I detect the changes, things like having a robust change management process in place. We want this transparency, and we want to be able to sort of go back in maybe years to come and show what was changed and why, having sort of comments and things like that sort of put in place. And also pre-assigning different type of rules for importing. We can configure that so they're there for reuse over and over again. The other thing we can do now is we can do sort of report generation. And then finally, I'm going to go over some of the supported formats, and then just going to wrap up with a summary just to reiterate some of the things that would have gone through in the previous slides. So some of the challenges people facing, we know that design complexity is getting greater. Things are getting smaller, and obviously with things getting smaller, there's less room for heat to dissipate, for example. Also from that, we're seeing things like connector positions and connector packages changing. This is sort of driven because people start to see they don't have access, and the connector needs to move because they just can't put the mating connector in place, or something is connecting to is in a different position and it needs to change. And then also, if you see the image on the bottom right here, you can see it's quite a complex housing. There's a lot of metal work in that. And with that, you probably estimate that there's a lot of heat. And this is where CFD comes into play as well, because what a lot of mechanical engineers do now is they'll be simulating airflow, for example, on the products. And what they will then see is that you might have to have certain channels for the air to cool certain devices down, for example, and also where the air is going to escape. And with that, what you then see is they know and can predict where dust is going to collect, for example. This means that in some cases, there might be some devices that will collect dust and could be sort of like harmful to those components. So what you then can do, you can predict that, and you can maybe add sort of conformal coating in those areas. So because of those sort of simulations that mechanical engineers are doing now, it means you then see more frequent changes because they're understanding the product earlier, and then getting things changed. The other thing we need is the ability to understand from one revision of mechanical data to another, and to sort of preempt and understand what is going to change. We've all been there. We've brought in a new mechanical data, and it's ripped up a lot of our work. So it's really good feature that you'd be able to sort of import the design, preview the changes, and then anticipate what's going to happen. You could potentially come out of the export or import, make some changes, maybe even move the connectors that's predicting to change, so you have control over how that connector will move and the tracking. Okay, and then also from that, we obviously need a bi-directional communication between ECAD and MCAD. It sort of needs to work both ways. So that's some of the challenges that people are facing at the moment. So we're going to go on to IDF. So we know this is an old format. It's been in use for a long time. But the capabilities is starting to get a little limited now in regards to the modern day electronics. We can import 3D objects, and we can have components placed automatically. We can create the board outline, etc. But it doesn't support any incremental reporting, and we also don't have the ability to reject or accept any changes. So what that means, I don't have any traceability on what has been done. So it's obviously that's a problem for us. Also, what you can't do with IDF is you can't visualize the import prior to importing it into your design. So you're sort of blindfolded a little bit, really, until you import it and see what it's done, in regards to ripping up maybe some movements and parts or things, and that's caused you a lot of problems. You may have spent a lot of time in those areas. So this is where the limitation is coming from. And then IDF isn't real 3D format data. And what I really mean about this is that, as you're aware, if you're a PCB designer, for example, or a hardware engineer is doing PCB design, if you're asking for IDF data from your mechanical team, it's an extra task for them. They have to draw those boxes, those squares and things like that, for example, to actually send you the data. So it's obviously taking up more of their resources, which you don't want to do. So that's some of the limitations on IDF. So I'm going to move forward now onto STEP. So as we can see on the right image here, this is a mechanical view of some mechanical data. And then if I import this into CR-8000, what I can see is I can now highlight all the objects that's going to come into my design. And then I can start sort of making some rules and understanding what it's going to do prior to doing that, okay? So that allows me to associate the MCAD geometries. It also allows me to extract 3D geometries from the data. So for example, in areas like this, it might be some sort of height limit. I can extract those height limits onto my PCB as inhibit areas, which obviously saves me a lot of time. And it also means it's from native mechanical data, so they don't have to redraw this type of thing again. And of course, I can import the board shape or update an existing board shape from the step file. But this preview that you have beforehand is very useful. Of course, what you can see here, I can cross probe from here as well to show which connector this is. For example, CN200, I can see it highlighted here. And then once I complete the import, the connectors now have been placed and the height limits have been generated into these areas, and the rest of my components are ready to be placed. So the other thing we can do with STEP, again, you can see the image of the native mechanical data. I have the ability, so I can, instead of importing and just seeing an image on my right-hand side and say, yeah, I can see what it's going to do, I can ask it to tell me the differences. And as you can see here, I can cross probe and you can see that this connector has moved slightly. And I have the ability to say, I can accept this or I can reject this, okay? Meaning if I reject it, it won't change my PCB. Of course, this then starts some dialogue with your mechanical team, because you can't just reject blindly and not tell anyone. You have to go back to the team and actually start talking to them, okay? It may be a reason they might be able to support you and say, yes, we can put it back to where it was because of the implications on the design, or it might just be a compromise between the two of you in regards to how far it moves, okay? And then once you've detected all the changes, I can then update the design and go forward from that. So here you can see that this connector has moved slightly. It's just updated design. It looks very similar to the original image because this connector is just a small movement. Okay. So importing mechanical data. So what we can see on the bottom here table, these are the type of things and type of objects that can come through from the mechanical data directly into the PCB data. So board outline and cutouts. So extracts the thicknesses and size from 3D models, detects differences in each cutout, allowing users to approve, import, or only approve objects. Automatically generate layout areas. We can import slots, square holes, non-circular holes, for example. And also, as I mentioned earlier, inhibit keep out areas. We can detect them and we can extract them and create those automatically onto the surfaces of the PCB or to the layers of the PCB. And then also the component placement, we can have those configured for us. So on the right-hand side, what you can see is I can actually create pre-assigned rules where I can go through different tabs. As you can see here, I have the board outline, component, arrow view, automatic registration, for example, and I can start to say, this is what I want to be able to do when I import this step files in future. So I don't have to, I can do this once and reuse the information. So reporting changes, we can do this. As I mentioned, you can do a compare. So you can compare from the design to new data, give you a graphical image of what is different, but also I can get a text-based report as well. This obviously can be used to just print off and maybe put into an electronic file or sort of hard copies or whichever you wanted to do. The other new feature in design flows, and this is handy if the mechanical team are plowing ahead and the hardware and electrical team and the PCB designers don't have a project yet. So the hardware engineer, if he can get or she can get a mechanical step file, you can take it into design flows without a project. So what that means is I can import the data, and even without the project, I can start to view some of the positions and the shape of the PCB. Now, where this is really useful is that a hardware engineer might recognize that CN200 needs to be used for a particular application. And the position that the mechanical team, because they're ahead of the curve really in regards to design process, is putting in a location that's going to cause problems further down the process flow. So by being able to preview this first, they can sort of head this off early in the design flow and start to say, this connector cannot go in this location because it's going to cause us a problem for whatever reason, EMC or whatever it is. The hardware engineer's experience would then say to the mechanical engineer that we have to change. But instead of seeing this maybe 2-3 months later, and you could also be seeing that the mechanical team has already maybe committed to tooling. If they've already committed to tooling, they've lost money. You lost money, you lost resource. So this early heads up, so the advanced visibility when you don't even have a project is crucial. It sounds a small thing, but it isn't. It's quite a big thing. So just moving from STEP onto IDX. Okay, so we can see it's an XML-based messaging format, IDX. On the right-hand side here, we got two different design flows, how this sort of fits together. So the mechanical design team starts a sort of outline on maybe some cutouts or some components in certain areas of the board and transfer the data through into the hardware team or the electrical design department. Okay, so this then is used as the sort of like the base or the starting point. And then once the hardware is becoming more mature, additional items and blocks and components or slots or holes or whatever it is being added onto the PCB each year. And this is moving along. But at the same time, the mechanical team also are making changes. So when they make changes along here, at other points here, I can send another file through into the PCB design team. And then this can be classed as incremental. So I can see what has changed from this one here, the base level, to this incremental, and I can have that in here. So I can see them in advance. Also, it's bidirectional, which means PCB design team or electrical design department have made some changes. They can compare against the mechanical team and then send back a response IDX through to the mechanical team as well. So as we can see, this is bi-directional process on how the MCAD team and the ECAD team can sort of communicate with each other. Okay, so just to go over some of the baseline, incremental, and response. So the baseline IDX, obviously you've got some information here you can read, but I'll just summarize it really for you. So the baseline IDX, this is just really creating like a snapshot. So a snapshot which will be used for reference when you import a future incremental IDX file. This will allow you to see what's changed, allow you to accept or reject the changes, and then send back a response IDX file. What's key here as well is that the baseline IDX file, you can bring in multiple baselines if you want. So if the design is quite fluid, meaning there's a lot of changes still happening, we mentioned this at the beginning, the mechanical team could be doing simulation and starting to see that they have to move things around very early in the design process. You may not want to document all of the changes. You may want to get to a more sort of like stable position and then bring in a baseline IDX file. And then after that point, start getting incremental IDX files, because it's more meaningful, the changes. When things are so fluid, having hundreds of sort of documented changes might not be useful for anyone. Of course, you can do it, but you don't need to. You can wait until the product is more mature, and then you can input a baseline, and then creating the incremental IDX, and of course, the response IDX going back. So the baseline IDX file, not a lot really to say here. You just import the IDX file. This obviously just creates the baseline, as I mentioned, and creates a further snapshot so that other people, when they import the incremental, will show the changes. Okay, so incremental IDX file. So when I bring this in, I can now start to see the differences between the baseline and what is now being imported. We can see here, we can say we accept this or we reject it. Obviously, if we reject it, we can then start to say the comment against that, why it's being rejected. And as you can see here, in the background, automatically, a response IDX file is generated, which you can send to the mechanical team. They will then see the comments. And again, of course, this starts dialogue. This starts the communication, which is so crucial in today's design flow. If your communication is poor, you'll get poor product out. So this helps you with that communication, because it tells the mechanical engineer what you've accepted and what has happened on the design. And of course, this rejection may not be the last thing there. They may say, we still have to do something. We can't get away with not moving this connector. It has to move something. And again, the dialogue means some compromise maybe between the two departments, but at least it's documented and at least it's communicated, and it's less likely to cause any errors. Okay. So this is the export of the incremental file. Like I said, we create a baseline incremental mode. So in here, we can specify what we'd like to do on the export. So this is sending out of the ECAD tool. So in here, similar flow to before. Now we've got design changes here, and we will send an incremental IDX file to the mechanical team here. And then obviously they can see what has been changed from the electronic side of it. So again, similar linkable objects, board outlines and cutouts, holes, inhibit areas and keep out rules, other layers, things like tracks and resist and silk, for example, or document layers that you may want to send back to communicate your design intent to another department. And then, of course, the component placement will automatically be done as well. So just going to go on to some of the supported formats. As Klaus mentioned earlier, we now support the JT format. Import and export. JT is a lightweight 3D data, which is generally used to exchange data between NX and Teamcenter. And then further here, these are the other sort of supported options if on the export and import. So CATIA data, Creo, NX, STEP, JT, as we mentioned, Parasolid. So these files are the native CAD system files that can be imported directly from the mechanical team. I'm not sure how I'm doing for time. It felt like I've gone very quickly, so I do apologize. So in summary, IDF is a very old format. several limitations, doesn't support us in our modern design flow of being able to communicate back and forwards between the MCAD tools. IDX is a newer format. Obviously, it's a convenient way which supports other ECAD-MCAD functions. And obviously, with the added advantage that bidirectional communication is possible. The difference between IDX and standard formats like STEP is that we can follow up with incremental changes, which electrical and mechanical designers can choose to accept or reject. And obviously, we can pass this information back, as we said. So that's my presentation finished. If there's any questions, please don't hesitate to ask them. Thank you very much.
So, for your presentation. Let me see if we have already got questions. And in fact, I can see a number of them coming in. First question is regards the thickness of the board information. Does it include additional layers like silk screen and solder masks, or is it only the bare board thickness?
So the thickness of the silk screen and solder mask, I don't believe comes through, because I doubt that will be in the mechanical data to start with. But I think I'll have to check that. I don't believe the thickness of those elements come through.
Okay. So something about flex rigid boards. Will the bend information also be transmitted? Is that possible?
So the bend information could be transmitted in regards to a line, and then obviously you configure that bend information within the Design Force tool.
Okay. Let me quickly take a look at the time. I think we are still well in time. Okay, so another question. Let me see. Let me pick the ones that looks most relevant. So is it also possible to read in placement areas from mechanical data?
Placement areas. So if I'm assuming you mean component positions, then yes.
Exactly, yeah. So indications where certain components ought to be placed or something like that. I don't know if it even makes sense to specify that in mechanical.
So the mechanical tool will have sort of step information, and they'll have component reference designators. From that links through into Design Force, and those reference designators will be recognized, and those part positions will get placed.
Okay. Do you know?
Klaus, sorry, one point I should add there, the coordinate system between the mechanical tool and Design Force needs to be set, so that they actually have the same base points and datum points.
Okay. Next question is, just a second. Do you know if IDX import-export is possible with CATIA V5?
So if you look at the supported, if I just go back up a page. So what we said, CATIA, so the output system, as we can see here, is CATIA V5. So it says it supports that version, yes.
And the last question is about integration with Creo Parametric. The question is, where would I be able to get more information or an in-depth guide on how to use it? Or is it simple enough to use? Is add-on software required, etc.?
No. So if I understand the question, I'm assuming that you're saying a mechanical designer can just export the native format. That's obviously done in the native mechanical tool.
Yeah.
So that's not my area of expertise, I'm sorry. But that should just be an export function. And it's very simple then in Design Force just to import. It's just under the Utility tab and import and select the format that you want to look for.
Okay. Anyway, we've got the name of the attendee, and we can come back separately via email
yeah.
and answer that question in detail. So no
Yes,
problem.
yeah, that's fine.
Okay.
Yeah.
With that, I have no further questions. I would like to thank you for your attention, and I would like to thank Paul for his presentation. We will be back at 11:30 with a presentation with the title Ensuring Business Continuity and Reduce Supply Chain Risk in PCB Design, Managing BOMs with DSCR and Silicon Expert. It will be presented by my colleague Nicola Kontic. We are closing now and hope to see you back at 11:30. So basically in something like 25 minutes. Thank you.
Thank you very much. Take care. Bye.